All right, so in the beginning, you learn F equals ma, and then when we go to conservation laws, we don't really derive those laws. I just tell you that there is this thing called kinetic energy or energy. So kinetic energy turned out to be 1/2 mv squared, and if you add it to potential energy, then I just tell you it's conserved without proving it. Also, I did momentum, which is mass times velocity, and tell you that it is conserved without proving it. And finally, we have angular momentum, which is also a conserved quantity. So you should be happy that I don't ask you guys to prove it. Otherwise, it will be harder for you to survive in this class. The reason I don't ask you to do that is because to prove it, you need to use something called Noether's theorem. So you need to thank this lady, Amy Noether. She is the reason that you have a easier time in the second half of this class. So what is Noether's theorem? Noether's theorem tells us that Low's conservation law comes from not from Newton's law, but from the symmetry of physics law itself. So let me translate that into English. First, let's look at this valley. This is a valley, and imagine you have a ball starting from here, and it starts rolling down, up, down, up. So it will just keep rolling along the valley. Let's say there's no air resistance, there's no friction, so the ball will just keep rolling, and it will not stop as long as the valley is uh, all the way going there without changing its shape, and it keeps extending in, let's say this is the x direction. So because you know the ball will keep moving in the x direction, it will oscillate in other direction, but the motion in the x direction is the same. So you know for this case, the x momentum is conserved. Okay, and this is because the valley is extending all the way along the x direction. The valley will look the same as you go along x direction. Now, when we look at the other case, this is another valley. This valley shapes like a ball. So if you put a ball starting here and push it to this direction, it will roll kind of up and down. But as it oscillates, it's going to go around the center of the cone. It's going to go around the center of the valley, and because the valley is like it's not going to have a bump in any part of it. It is smooth, so it will just keep circling around the center of the valley. So because you know it's going to keep doing that forever, the angular momentum, which is how it is going around the center, is going to be conserved. So in this case, the angular momentum of the ball is conserved because the valley has so the valley looks the same when you rotate it. If you stand at the bottom of the valley and then you look toward this direction, that direction, there, here, the valley looks the same in every direction. And if you rotate yourself, the valley looks the same. This is why the angular momentum of the ball is conserved. Okay? All right, so Noether's theorem say that the reason that this momentum is conserved is because the valley looks the same along the x direction. And if we say it in a more formal way, we say the valley is symmetric under shifting x, which means that if you shift your position along x, the valley looks the same. All right. So if you start from here, look around, the valley looks like this. If you go further along the x direction, you look around again, the valley still looks like this. The valley looks the same when you are shifting your x position. So we call this a symmetry under shifting x. Okay? And it says that as long as you have this symmetry, you have conservation of x momentum. So Newton's theorem tells you that this conservation law comes from this symmetry. All right? Now for this cone, the valley looks the same when you rotate yourself when you are standing at the bottom. When you are standing at the bottom, you look this direction, this direction, this direction. The valley looks the same no matter which direction you're looking at. And we say this is a symmetry under rotation. So you learn that angular momentum is about rotation. So I hope it makes sense that this rotational symmetry will give you angular momentum conservation. Okay. So this is Newton's theorem. Newton's theorem says that the conservation law will come from the symmetry of your surrounding. As long as your system has some symmetry, it will have conservation law. Now, when we start a class, we say that physics should work the same for anyone at anywhere at any time. That statement actually corresponds to the symmetry that physics law should have. Physics law should work the same when you are standing here or here. So when I'm standing here, I do some experiments, I learn the physics laws, and the physics law I found when I'm sitting here should be the same as those I found when I'm standing here. I can shift my position in the universe, and no matter where I am, the physics law I found should be the same. So physics law should have this symmetry under shifting my position. So when we say give me extra page. So when we say physics works same under or at anywhere, everywhere, just say everywhere, can spell. So this statement actually means that physics law should have symmetry under shifting x, y, and I assume you only learn x and y, so let's stop at there. So because physics law should work the same everywhere, we don't need to go to Newton's law. Just by knowing that we are doing physics, we for sure know that we will have conservation of x momentum and y momentum. This conservation law does not come from Newton's law. It comes from the fact that we're doing physics. Okay, so let's know the theorem. It tells you that conservation law will always be there as long as you have this symmetry. So if one day Newton's law turned out to be wrong, it doesn't mean that conservation law is not there, because conservation law does not come from Newton's law. It comes from this symmetry. Any questions so far? And we also said that physics law should work the same for anyone, for everyone. So we can think of it as one person standing here facing this direction, but another person is facing another direction. No matter which direction you face, the physics law you see should be the same. You never need to do your physics exam facing a particular direction, otherwise you'll get a wrong answer. So you know physics works the same in every direction. And that corresponds to that physics law should work the same for everyone. So it is telling us that physics law should be symmetric under rotation. So it gives us angular momentum conservation. Angular momentum conservation, again, comes from the symmetry itself. It's not from Newton's law. So even though Newton's law is wrong in many cases, as you will see later, angular momentum is still conserved. Okay? Finally, we have energy conservation. And what does that correspond to? So if you look at the shape of the valley is not changing when the ball is rolling. There's no earthquake. Have you guys been in any earthquake before? Okay, so earthquake is when the land is moving. If the land is moving, let's say originally you have a mountain like this, and the ball is at here, and there's earthquake. So the shape of the mountain changes. You have a rise of your land, and you see the height of the ball changes after earthquake. And if you know the ball goes up, the potential energy will go up or down? Or go up, good. So you see that in this case, energy goes up, it's not conserved. This is because that the shape of the valley is changing with time. This is why the energy of this ball is not conserved, because the shape is changing with time. Now, when you look at these two valleys, the shape of these two valleys is not changing in time. And you know that this ball will keep rolling in this direction, and this ball will keep rolling around the cone. While they are rolling, the speed is changing, but the speed will increase when potential energy decreases when it rolls down the valley. And the speed will decrease as the potential energy increases when it goes up the valley. So if you look at the total energy of the ball, it's actually constant. You see that for both of these things, you don't need this anymore. So because the valley is not changing with time, we say the valley is symmetric under time evolution. It means the valley today looks the same as valley yesterday and the valley tomorrow. It's symmetric after you shift your time or after some time has passed. And this symmetry corresponds to energy conservation. Okay? And we learned that in the first class, physics law should work the same today, yesterday, and tomorrow. So this corresponds to symmetry under time evolution. Which tells you that energy will be conserved. So that is Noether's theorem. I'm not going to prove it to you guys, but the idea is that because physics law have this symmetry, so you are guaranteed to have these conservation laws. They do not come from Newton's law. the conservation law comes from the symmetry. And Noether's theorem is telling you this fact that symmetry gives you conservation laws. And these conservation laws are important, so I hope you guys know why Noether's theorem is important. Okay? Any questions? 9 questions away from me doing fair. All right, so this is our lady, Amy Noether. She's about the same time as Albert Einstein. They have a couple of conversations when they are alive. She's the reason that you need to learn conservation law. So if you hate Newton, you should hate her as much. And if you think Newton is important, you should think she is important equally to Newton. Yeah, so Noether's theorem is published in 1918. People kind of know conservation law before that, but they do it with Newton's law. You can show that the kinetic energy you learned is conserved with Newton's law, but the proper way is to use Noether's theorem, because even though the kinetic energy you learned, so in real life, the kinetic energy you learned is actually not conserved. It will be conserved in your exam, so don't get confused. But in real life, if you try to accelerate some particle with higher and higher energy, you will see that the velocity will not grow like this. And so you know this is not the true conserved quantity. But it doesn't mean that conservation law is wrong. It just means that Newton's law is wrong, because conservation law comes from the symmetry, and as long as the symmetry is there, energy is conserved. It's just going to look different. I can show you how it should actually look. It should look like 1 minus v over c squared with a square root, 1. So you don't need to know this, and you don't need to memorize it. Not like I'm just making I'm just giving you a idea what kinetic energy should actually look like. It still depends on your speed, but there's this constant, which is some velocity. You know, it should be some velocity or some speed, because you learn dimensional analysis and you see I am subtracting 1, a dimensional number, with this ratio. So if I'm subtracting 1 with this ratio better be dimensionless. So you know c and speed has the same dimension. And this constant is about 3 times 10 to the power of 8 meter per second. So this is how this is the energy that is actually conserved. This is because conservation of energy does not come from Newton's law. It comes from the symmetry under time evolution. Okay? So in the beginning, let me get rid of a lot of distractions. Let me not let this thing distract you. Goodbye, goodbye, goodbye. Hey. Good, so in the beginning, I told you this statement in the first class that physics law should work the same for everyone, anywhere, anytime. And to translate that into English, we learn about reference frame. And this statement means that physics law should be frame dependent. It should look the same for everyone. So it's the same for every frame. But we learn that if you go to a frame and you try to do position is not frame dependent. The position of this chair looks different for me and for you guys. It's not frame dependent. The velocity is also not frame dependent, because if I start moving, the chair is moving, but for you guys, the chair is not moving. So velocity also depends on the frame. And finally, we go to acceleration, which will be the same under all the frame as long as your frame is not accelerating. So we don't have enough knowledge, or we are just not good enough to have something that is truly independent in all frame. So we just try to make our laws independent in inertial reference frame, which is defined by Newton's first law. As long as your object getting no force will stay rest or move with constant velocity, then we know your frame is a inertial reference frame. That's what Newton's first law is about. Then using the acceleration, which is the quantity about motion that is independent in all the frame, we know it's going to work because if satisfy the symmetry, it is independent in all the frames. So we know it should work, and force should be related to acceleration. You learn F equals ma, not F equals mv, because you know there's no way for force equals velocity. Force is the same for everyone, but velocity looks different for different frames, so it must be acceleration. And then you have your Newtonian mechanics, that is what you learn for your midterm, right? Good. And how about the conservation laws? Now you learn that the conservation law comes from the symmetry of inertial reference frame. For non-inertial frames, there's no symmetry because you can do weird things, but just for the frames moving relative to each other with constant velocity, they satisfy the symmetries. So you use Noether's theorem to derive the conservation laws. So you know there's going to be a thing called momentum, which corresponds to the symmetry of shifting your position. And there's going to be a conserved quantity called energy, which corresponds to time evolution. If your law doesn't change today, yesterday, and tomorrow, then you know energy should be conserved. And if your physics law works the same when you rotate around some points, some axis, then you know that you should have angular momentum conservation. You know those conservation laws are there, you just don't know what exactly is this conserved quantity. So then you use something that you know, like Newtonian mechanics, and you try to find what is this conserved quantity in Newton's language, and you found that the conserved energy or kinetic energy turned out to be 1/2 mv squared, only under Newtonian mechanics. If you are not using Newton's law, energy may look different, but it's still conserved because conservation of energy comes from Noether's theorem and the symmetry of our universe. Okay? Similarly, angular momentum and momentum may look different under different framework. Newtonian mechanics is a framework. You calculate your motion under this F equals ma thing, and then if everything follows F equals ma, then this too will be conserved. But when one day F equals ma doesn't work, then this too will not be conserved, but there will still be some conserved quantity. It's just that they look different from what you learned in Newton's law. For example, another famous physics law is called quantum physics, quantum theories, quantum something is quantum theories. The way that quantum theory approach this problem is by looking at the probability for something to happen. The probability for something to happen is the same for everyone, anywhere, anytime. So if I flip a coin and I ask every people in the universe what's the probability of getting a head and a tail, they will all agree it's 50-50 or some number if the coin is not fair. But you know the probability will be the same because you can just count how many times you get head, how many times you get tail. Everyone will get the same count, so probability is actually a frame dependent thing. That's how quantum theory approaches this problem. It's weird because we are looking at some probability, but if you think about it, there's nothing more symmetric than probability, so you are guaranteed to have some success. And indeed, we have most of our success in modern physics in quantum theory because we found the right thing to describe our universe. Instead of describing acceleration, we describe probability, which is even more symmetric than acceleration. Okay? So if you use this framework, then you know it's still going to have this conservation laws because you still have a symmetry. It's just that the conserved quantity will look different. In Newtonian mechanics, energy looks like this, 1/2 mv squared. And if you use quantum theory, energy looks something like this. This is H psi equals energy times psi. H is something called Hamiltonian. You don't need to know what that is. Psi represents the state, and this is how energy looks like in quantum theory. So no matter which theory you are using, there's always going to be conservation laws because those conservation laws comes from the symmetry according to Noether's theorem. That's why Noether's theorem is important. It's just that the conserved quantity will look different under different framework. But you know there's always going to be this conserved quantity as long as your physics law is symmetric. Any question? And finally, remember that we said if you are Einstein, you can just go from the space-time curvature, and then space-time curvature is independent under all frames, and you can study the gravity with black hole and stuff. That's called general relativity. The thing is that if you have a black hole, or if you have space-time curvature, this curvature will break the symmetry of your spacetime. When you are standing here doing your experiment, and you are standing here doing your experiment, the physics law will be the same. But if you are standing next to a black hole, the physics law you see will be different because black hole is there. Black hole is about the spacetime itself, so the spacetime near the black hole is different than the spacetime here. So it's not symmetric. You don't have this symmetric under shifting. So energy is not conserved, momentum is not conserved, blah, blah, blah. But as long as you are away from a black hole, you will approximately have this conservation law. So that's all about Noether's theorem. You guys good for your homework? Okay, good. So now let's look at some phenomenon that breaks Newton's law. So this is my laptop. If you zoom in, you will see there's a chip. And if you zoom into this chip, you will see that this chip is made by spherical objects. It's not made by point-like particles. In Newton's law, we say that everything is made by point-like particles, so we can build up everything from there. But if you actually zoom in and look at what everything is made of, you see that they are made of tiny little balls. This is the actual experimental picture of the atoms. Yeah, so we call this balls atoms. I believe you guys know what atom is. Somehow you learned atom. Good. So atoms look spherical, right? It looks like balls. Good. And these balls are really small. If you look at the scale, this is 1 nanometer. 1 nanometer is 10 to the minus 9 meter, so it's really small. And if you look at atoms, you see one atom is smaller than 1 nanometer. So we say the scale of atom is about 10 to the minus 10 meter. So you see they are very small, but they are not points. They are not point-like particles. And if you look, so you might think, all right, atom is not particles, but maybe it is made with particles. So to see if the atom have any internal structure in it, you can blast it with some radiation. So this is a element called radon. It's like a gas under room temperature. You can trap a gas. This gas will emit some radiation. You don't really need to know what those radiation is. You just need to know if you put your hand here, it hurts. So you know it is emitting something out of the gas. So the trick is to blast a gold foil with this radiation. The reason we use gold foil is because you can hammer it so it's really thin, so that there's only like a few layers of atom in the gold foil. We want to study the structure of atoms, so it's a good idea to have only a few layers of atom. Now, what happens is that when you blast this gold foil with radiation, you see that most of the radiation just pass through. But some of it will bounce back with a big angle. So what does it mean? It means that the structure of atom is not uniform. If it is uniform, then the radiation will just all be weakened by some factor. But the fact that most of them pass through shows that atom is mostly empty, or most of its mass, the mass of atom is definitely not distributed uniformly throughout the entire ball. And we see that some of the radiation will just bounce back. This means that atom has some core which all the mass is concentrated. Okay? So this is what this experiment tells us. It tells us atom has a core. So this is called the Rutherford's gold foil experiment. You just need to know Rutherford because that's how everybody calls this experiment, and it's like everybody know what you're talking about if you say Rutherford's experiment. So if you want to know the structure of something, you just throw high energy particles, high energy radiation to that thing. That's still how we study physics until now. Anyway, so we see that atom is made by something. It is made by a jacket, so it looks like a ball, but inside the jacket there's a core. And even though it is a small core, you can still measure how big the core is. You can do this experiment, count how many radiation was bounced back, and the more it bounced back, the bigger the core. So the number is that an atom is 10 to the minus 10 meter, and a core, or we say nucleus, the nucleus of the atom is 10 to the minus 15 meter. So what does it mean? It means that if you make this atom bigger, if you just scale this atom up until it is as big as this room, then the size of the nucleus is the tip of my Apple Pen. This is how big a nucleus looks like if atom looks this big. Okay? So you see it is very small compared to the size of the atom, but it still has a size. It's not a point-like particle. So we know that atom is not a point-like particle, and it is not made by a point-like particle. Our current understanding of atom is something like this. This is atom. We know it has a core. It looks spherical, and the spherical structure comes from a jacket. This is not up to scale because you know the nucleus should be a lot more smaller. So if I draw it up to scale, the nucleus will be invisible. But you know there should be a core. There should be a nucleus. So You guys might have learned that the jacket that the atom is wearing is called electron. You guys heard it? Okay, so electron looks like a jacket when it is around the nucleus of the atom. It is a quantum particle, which is not a particle. Quantum particle does not behave like particle at all, so you can just say it's not a particle. Electron is not a particle, it's a quantum particle. A quantum particle can look like a jacket, but a particle cannot. You guys learn something like a atom is a core with a electron flying around it. That's how you guys learn about atom, right? So you know it's wrong because atoms looks like a ball. It is spherical. As you can see from the picture, they are kind of fat. If atom is like a solar system with electron orbiting around a core, it should look flat like a pancake, right? But you know atom does not look like a pancake. So there's no way that this is correct, and indeed this is incorrect. The real atom looks something like this, and electron is not a particle. And to understand how this structure looks like this, you cannot use Newtonian mechanics because first of all, it's not particle, and you just don't know how to do F equals ma with this jacket and the core. So this is one phenomenon that Newton's law doesn't work. But energy is still conserved. The energy of atom and how you interact with it will still be conserved. It's just that it looks different. It looks like this, okay? So, any question about atoms? All right, so this is a atom. If you have a lot of atom, this is a element called tin. So if you have a lot of atoms, you can stack them and give you a microscopic object. You can stack the tin atom in different way. These two are basically the same, but you just stack it with higher gap or smaller gap. The thing is that they are the same atom. They are the exact same stuff, and you just stack it with different ways. If you stack it closer, you get a conductor. If you stack it far away, you get an insulator. Is tin an insulator or a conductor? It depends on how you stack the atoms. Do you guys know what is conductor and insulator? If you have a conductor like a metal fork, you should not put it in the socket. But if you have a plastic fork, it's fine. A plastic is an insulator which cannot conduct electricity, but a metal looks like this will conduct electricity. So don't put metal fork in the socket. The thing is that they are the exact same atom. All you did is to make their gap closer, and then suddenly insulator becomes conductor. There's no way you can use Newtonian mechanics to explain that. You say, all right, there's a lot of particle moving around, but how can this particle give you conductivity but no conductivity when the gap is far? It's not that the conductivity becomes smaller. It goes to none. It goes from having conductivity to have no conductivity. Yeah, Pablo.
So is B same or is it just a different element?
It's the exact same element, exact same atom. Beta is for the structure. So these two are both tin atom. The atom is exactly the same, but you just stack it differently, and the result is different. Good job. We are now 22 in question count. Your goal is 30, all right? So, yeah, that's why, Newton's law must be wrong in the scale of atom. But if you are looking at something that doesn't it's not related to the nature of atom, then you'll be fine. You can say, all right, now I have a alpha team and I have a beta team. If I drop them at the same time, which one will fall to the ground faster? They will hit the ground at the same time. You learn that. It has nothing to do with conductivity. So if you are studying the motion of these balls, if you just throw a piece of alpha team, you can calculate trajectory with projectile motion, and same for beta team. So this is the phenomenon that is not related to atoms' nature. If you are just looking at their motion, then you don't need quantum mechanics. But you know, just Newton's law is not enough because there's no way you can explain how the same atom just give you different property if you stack it differently. So if you want to know why this is true, you need to learn quantum mechanics. Okay, that's the second phenomenon I want to show you. Finally, we have your sense of smell. Here are three molecules. Molecules are atoms combining together. And this is called benzene, something like that. Anyway, you should be able to see that this two looks different and this two looks very similar. So what does they smell like? It turns out that this two, which looks very different, both smells like bitter almond. They look different. There's no way they smell the same, but it turns out they smell the same. Okay? And when you look at these two different molecules, the difference between them is that the atom in the center is different type of atom. One has like iron, one has nickel. But you see they pretty much look the same. And iron and nickel is like next to each other in the periodic table, so it's basically the same atom. But this one smells like hot pepper, and this one smells like oil. Your nose is a quantum sensor. This shows that the sense of smell cannot be explained just by F equals ma. If you use F equals ma, they have pretty much the same m. They look the same, so F is the same, A is the same, the result should be the same. But no, that smells very different. And these two looking very much different, smells exactly the same. The sense of smell is the only quantum sensor you are born with. So if you want to learn quantum mechanics, you know it's going to be interesting because you can smell so many different flavors when you're eating something good. This is from his paper. I need to give credit to him. Yeah. So those are all the three phenomena I want to mention. Any question? You good for your homework? All right. So that's all for this summer session. Let's take a 10 minutes break and